Welcome back, class. So let's continue on with the amplifiers chapter or topic. And we were doing BJT amplifiers first. And I walked you through a lot of the theory on the three configurations, the common emitter, the common base, and the common collector. So it's time now to look at problems related to each one of these. So let me keep moving on my presentation to the first numerical example or problem, and that's on slide 18 of my PPT. So here on slide 18 we have example 617 from the textbook. This is on page 430. So it's an example, that means the solution is available in the textbook, and I don't feel I need to go too deeply into it, but just briefly look at what the problem is. So it's a CE amplifier, basic CE amplifier, the BJT with beta equals 100, and the early voltage VA is also given. It is biased at 1 milliamp. That means the IC DC biasing current through the collector is 1 milliamp, and it has a collector resistance of 5 kilo ohms RC in the collector circuit, right? So you have to find the three main important amplifier parameters, which is the input resistance, the output resistance, and the open circuit gain. Next, we are told that if a load is connected, now it's not open circuit anymore, it has a load, RL 5 kilo ohms. Similarly, the signal also is connected, and it has a resistance, an internal resistance of 5 kilo ohms also. So if these two are connected, then find the resulting AV and GV. That means the voltage gain with the load connected, and then GV, which is the overall voltage gain, which is the output divided by the signal voltage, right? So that also has to be calculated. Lastly, if V pi, that means the voltage here is to be limited to 5 millivolts, and this little, the way he's written it, it's the signal voltage. If that is to be limited to 5 millivolts, what is the corresponding V signal and V output, right, with the load connected? That means with RL being connected. So these are the 3 or 4 things you have to do, and it's pretty straightforward. If with all these formulas being available to apply one after the other, you can find all the necessary things, right? So first and foremost, you got to do these GM, R pi, and RO, and this is just straight mathematics. Then Rin becomes R pi, so that's what is required. AVO is this, which is about 196, I think, and then output resistance is RC in parallel with RO. Then you can find the gain, voltage gain with the load resistor in place with these formulas, and then you can find the overall gain, which is the output voltage divided by the signal voltage, using this formula. Lastly, if a voltage is given here, then what will be the corresponding voltage? It's like the reverse of the voltage divider formula, which is what is used here. And once you know the V signal, the V output can be found. Okay, so pretty straightforward. Look through the steps, make sure you understand. This is a very important example. It's the first example in this chapter, so you need to become comfortable with these numbers with being able to apply these formulas, because the rest of the chapter, all the problems are going to look similar, right? Okay. Example 618 on page 435 is a continuation of the previous example. Now the CE amplifier has a resistance Re in the emitter circuit. So if you include a resistance, then we know what happens is the input volt resistance Rn increases, right? So why does it increase? Because we use this formula. Previously it was just Re, the small Re, but that now becomes this, and so the input resistance goes higher. There are other benefits also, but for now I think we are focusing on this increase in resistance. Also, this part is interesting. Now if you want to limit the input voltage V pi to 5 millivolts, what are the corresponding values of V signal, right? Previously we got the V signal to be 15 millivolts, or roughly that. Now you'll find the V signal to be roughly 50 millivolts. So you can see how much it has increased. That means you can apply a larger voltage swing on the V signal and still not drive the transistor into saturation. So that's the benefit, right? The output voltage stays about the same because the gain falls when you introduce an RE, but the advantage is it's more stable. If you take different transistors from the same family with different betas, they will all work in the linear range and not go into saturation, even if you have a higher V signal. So that's the advantage of a CE amplifier with a resistance in the emitter circuit. Alright, let's move on to the next example, which is also an example, next problem, which is also an example on page 443. Here we are designing a emitter follower or common collector circuit. So this, we have seen this particular unity gain buffer amplifier before, and now the problem is for us to use, now remember this is just a theoretical amplifier, right? Now he is telling us take an actual NPN BJT and make this circuit, create a circuit, right? So that's what we have to do, and the values shown here, the 200 millivolts on the signal, the resistance of the signal source 100 kilo, a load of 1 kilo, is all duplicated. It's the same thing. And remember also that the gain should be 1, right? Unity gain. So all that is given, and we have to design, meaning we still have to find the IE, the bias current, and the minimum value of the beta that the transistor must have. Also determine the maximum allowed value of V signal if V pi is to be limited to 5 millivolts in order to be in linear operation. Lastly, given a certain V signal, 200 millivolts, determine the signal voltage at the output. If RL is changed to 2 kilo ohms, so right now we've got RL as 1 kilo, then if it's changed to 2 and then to 0.5. Okay, so for all these you have to design, you have to find the bias circuit, etc., bias current. So the formulas to use I've shown here, RO, RE, Rin, the overall gain, V out by V signal. This is the formula. If you have a resistor in the, sorry, for the emitter follower. Um, there's not much. Hold on, let me see if there's anything more I need to tell you. I'm looking at the textbook. IE comes out to be 2.5 milliamps, using this. So first we have RO is specified to be 10 ohms. So using that in this formula, you get NVT is 25 millivolts. You know that. You get IE, which is approximately also IC. The input resistance can be found like this. It comes out to be, input resistance is given, right? So beta is what we find from here, and it comes out to be 98. All right, there's really not much more I need to show you. Uh, the overall GV comes out to be 0.5. Remember, GV is including the load resistance, right? So that's not unity. Unity is only this portion um, without the load and all that. It's the open circuit voltage gain. So that's 1 always. All right, nothing more here. I will let you read through it. If you have any questions, let me know. All right, let's look at the first of the problems from the back of the chapter. And this is, okay, I'll leave it here. So it's a similar problem as what we have seen, except that it's from the problems in the back. It's an emitter follower, or common collector, and the biasing current is given to be 2 milliamps and beta is given. There is a source with 10 kilo ohms resistance for the source, and a load is also given 0.5. So with all this, find Rin and these two gains. VB is actually, I don't know why he V at the base, I guess. So instead of using VI or something, he's confusing us by introducing VB, but this is what he means by VB. So VB by V signal, which is just this area, and then V output by V signal, which is this by V signal, which is GV. So find all those. If the signal amplitude is to be limited to 10 millivolts, so the signal, if it's to be 10 millivolts at the base emitter junction, what is the corresponding amplitude of V signal and V output? Find the open circuit voltage gain and the output resistance R out. Use these values first to verify the value of GV obtained in A, and then to find the value of GV if RL reduces to 250 ohms. So a bunch of things have to be done. Here are all the formulas: Rin, Re, small re, uh, this gain VB by V signal. It's a ratio, it's not even the gain, it's just the voltage across this part. Then the overall gain, V output by V signal, here's the formula. Then we need to find GV in a different way, right? GVO is 1. So GV can be found like this, but you need R out to do that, and R out for a common collector comes out using this formula. Okay, so these are the steps to do it, and here is my PDF that you all like so much. Pardon my handwriting, but I hope I can walk you through this so there's no confusion. Okay, so problem 785, biasing current is given, beta is given, R signal is given, RL is given. V base is Rin by Rin plus R signal into V signal. Re first is what we need to find. Now we need Rin to do this. Rin you have to do using these formulas. First you need small re, which is this, which is 12.5. Then Rin becomes 51.76 using the reflection formula, right? This is the load resistance, it gets reflected over here. Then VB by V signal is 0.84 using this, I guess this formula. V output by V signal, it's the overall voltage gain. This is the formula and it comes out to be 0.82. Okay. The maximum VB is 10 volts, 10 millivolts. So the voltage across RE is 10 millivolts, assuming this voltage or this model, the T model. So we want the VBE to be maximum at 10. That means the signal voltage can be 0.4 because a lot of the signal gets dropped, right? Sorry. First we are finding the output voltage V0, right? The signal voltage actually comes out at the next step as 0.488. But first we find the voltage across RL because we know IC. So if you multiply IC by RL, you get the output voltage, right? The IC formula is here, VBE, and I think I show it, right? IC is VT by IE. So that's how we get IC. Then, sorry, it's actually alpha times IE. That's IC, okay? All right. So we know VO. Now, by definition, gain equals VO by V signal. So we know VO. We know gain is 1. Sorry, gain is 0.82 as found here. This is the not the open circuit gain, but gain including RL, the overall gain. So we get V signal to be 0.48. Now we have to verify that what we got here is right. So open circuit gain is 1 for emitter follower. R out is RE plus this in the formula. So you get R out to be 111.5. So using GV equals this, you calculate GV again as 0.82, which is the same as in what we found in A. Okay. Now if RL changes, then GV changes. It drops actually to 0.69 volts per volt. Okay. So I hope this was clear, and we can move on to the next problem. So that was 785. Let's move on to an example related to biasing, and this is on page 449. Okay, so give me a second, I will move to that example. Okay, so we want to design this. Now I told you that this is one of the most commonly used biasing circuits, at least for discrete BJT applications, and we must become comfortable with all these formulas here, because a lot of the problems I'm doing are based on this model. Okay, so there is one nice example worked out for you, 620 on page 449, and so make sure you spend some time and get comfortable with all these formulas. So what is the question? We have the voltage divider network. The IE here, IE is given to should be 1 milliamps, and VCC is given 12 volts. The beta is given as 100. So just based on this, you have to design the bias network. That means you have to find R1, R2, RE, and maybe also RC. So all these values need to be found. That's basically what it is. Okay. So he shows you how to go through this, and he starts with a nice rule that we should all understand very well. And the rule is that if this is 12 volts VCC, then we have three places that this voltage drops, right, on this path. It drops across RC, it drops across RE, and the remaining drops between the collector and the emitter, right, VCE. So he says, let's drop 1/3 of 12 here, here, and here, 1/3 each. Okay, and using that, how do you go about finding the voltage at the base, at the emitter? He shows you, right? And make sure you understand that particular system, because you'll probably use that quite a bit. Okay, so based on having established the voltage at the emitter here to be about 3.3 volts, and knowing that the current should be 1 milliamps, he shows you that you first calculate the value of this RE using Ohm's law as 3.3 kilo ohms, right? Then you have to design R1 and R2, right? So he picks a voltage divider current here as 0.1 times RE or IE. So you get that to be 0.1 milliamps. And using that, he comes up with R1 plus R2 as 120K. Then he also uses another method to come up with the R1s and R2s. Okay, so make sure you understand how exactly he does the logic of that and finds the individual R1 and R2. Okay, then towards the end, he also calculates RC. Okay, yeah, so I will let you look through these steps, and if you have any trouble understanding how he got these individual resistances, it's a little bit of a back and forth process. In the middle of this example, you can see how he checks the IE using the values he just got for R1, R2, then decides they're not very satisfactory, so he goes back and changes it a little bit. Okay, so it's a what we call an iterative process, but the process is not too difficult, so I will let you look through the example. Okay, all right, let's move on to a problem from the back, problem 7108. Here also we have a BJT with a beta given of 100, and we have to find R1, R2, RE, RC, right? Another important thing here in this example is that if the beta, which is nominally 100, that means that's what the manufacturer tells you is the average value of a beta, but the beta values for the transistors of that family can be as low as 50 or as high as 150. So even if the range is this high, we need to find the appropriate value of the resistances so that the bias current stays within plus or minus 5%. It should not change It should not vary more than plus or minus 5%. So that's a requirement. So how do you go about finding the right R1, R2, RE, etc., so that you're guaranteed that the bias current stays, it doesn't vary too much. Okay. Then if the resistance ratio as shown in A is used, find an expression for the voltage VBB, the voltage here, that will result in a voltage drop of VCC by 3, whatever is here, 1/3 of that across RE. For VCC is equal to 5 volts, find the required values of R1, R2 and RT to obtain IE equals 0.5 and still satisfy these two conditions above. Find RC so that VC equal to 1 for beta equal to its nominal value. So that's part A, B, C, D. Check your design by evaluating the resulting range of IE. So the formulas to use I've shown you here. IE, this current here, can be found as this through this circuit. VBB minus VE by RE plus RB by beta plus 1. Or you can, same formula can be written like this. There's also another formula to find VBB, which is the voltage here. Based on VCC, it's this. Now what is RB? We've talked a lot about RB. It's nothing but R1 and R2 in parallel, right? Lastly, here's another important KVL on this circuit. VCC is VCE plus ICRC, right? From here to here only. Okay, so using all this, let's look at 7.108. So B nominal is 100, B high is 150, B low is 50. IE must be within plus or minus 5% of nominal. So what is IE nominal? This is the formula. IE high, this is the formula. IE low, this is the formula, and this must be less than or equal to 5% above and less than or equal, greater than or equal to 5% below. Okay. So using 0.95, this lower formula, IE nominal by IE low, you can write it like this. You can solve this to get that ratio of RB by RE as 5.73. With this ratio of RB by RE, let's check. So IE nominal is this. IE low is this, which is 0.95. IE high comes out to be 2% higher, which is also within the range. So this and this, we put a check mark to say, yep, we satisfy the condition. Okay. Now, can we find that IE? Yep, that's the goal. We'll find it soon. Hold on. Yeah. Let's continue. So IE is this formula. So IERE, you multiply the current by the resistance, you get the voltage drop. So that is this, right, across the emitter resistance. Sorry, this RE I think is a mistake. I should take that out. Yeah. Because if you're multiplying both sides, then obviously this goes away. So I'm sorry, I don't know why this doesn't exist. Okay. So voltage drop is, and now this voltage drop has to be VCC by 3, right? That's given condition. So if you simplify that, you get this equation. VBB is VBE plus 0.352 VCC. Okay. So that's part B. Find an expression for the voltage, VBB, right? So that is the expression for the voltage. And part A, we needed this RB by RE ratio. We found that. to be 5.73. So we've done part A, part B. Now part C, if VCC is given to be 5 volts and IE must be 0.5 milliamps. Now VBE, remember, is just the diode forward drop, which is 0.7 volts always. So we can write this equation VBE and we come up with 2.46 for VBB. To find RE, you can use this. IERE is VCC by 3, so RE equals, this calculation, and gives you 3.33. Now using RB by RE is 5.73, you can find RB also. Now this 19.08 RB is actually R1 R2 by R1 plus R2. Now you can guess for some values of R1 and R2 to satisfy this, but there's another way to find it. So VBB we know is VCC times R2 by R1 plus R2 using the voltage divider formula. Just on this portion, right? So substituting all that, you can first get R1 as 38.8, and then based on this you can get R2 also. Okay. All right. Lastly, D, writing KVL for the collector to emitter path, VCC equals this. Given that VCE should be 1 volt and VCC is 5, what NIE is 0.5. So IC is alpha times 0.5, which is beta by beta plus 1, 0.5. Beta, use the nominal value of 100. You come up with the value of IC. So substitute all this in this equation. The only unknown is RC, and RC comes out to be 8 kilo ohms. So I'll leave you to check this. Use the values of R1, R2, RE, RC to check VBB, RB and IE values found above. Okay. So I hope this example is clear. It's a little bit complicated. Make sure you go through each of the steps and understand how we designed and came up with R1, R2. Design problems are tricky. They always require you to be a little creative in setting up formulas and all that, setting up equations. So I hope the two design problems, one solved problem that was done in the textbook and another one that we just did, it helps you to understand the design techniques. Okay. All right, let's move on. I got a few more to do. Exercise. So now we are in this section called 6.8 called discrete circuit BJT amplifiers, and I told you that here this is the last section in the textbook. I mean, there's a frequency section after this which we are ignoring for now, but in this section you have examples of each type of amplifier, and the examples or the problems will use all the techniques we have already learned in the past in this chapter to again create some real circuits. Okay. So here are a good summary if we are only dealing with CE circuits, well, any type of circuits. This is, with a constant current source biasing, but the formulas are still the same. So some important formulas to immediately understand. IC is generally alpha times this fixed value. We talk about VC here, we talk about VE here, and here are some formulas. We talk about the base current, we talk about this base resistance RB. Now if this is a voltage divider, then RB is R1 R2 by R1 plus R2. The base voltage here and how it's related to the current and the base resistance. This drop is generally fixed. It's a diode drop, is about 0.7 volts. How to find IB, right? So all these are techniques that we'll use later on. Now, we've talked about coupling capacitors before. Remember, coupling capacitors have no use, meaning they're open circuits for signals. They're only important for biasing, right? Sorry, they're only important for when signals are being considered, because signals are AC signals. So the capacitors have a path. If you're talking only biasing design, then the capacitors can be neglected because they are open circuits. Okay. So for a common emitter amplifier, here are the formulas. Here's how you use the pi model. If it's a CE with an emitter resistor, we use the T model, right, like here. All right, so all these techniques we're going to use. Now, the first example or problem I'll show you is actually from the 7th edition of the textbook, because there weren't any good examples in the 6th edition, so I went and copied it from the 7th edition. That's why you see this 7.40. And I'll walk you through the exercise, both 7.40 and 7.541. This is a normal CE. This is a CE. Yeah, they're both the same. Yeah, the next. All right, that's it. Let's do this first, okay? So this is a regular CE circuit with a VCC of 15 volts, beta 100. VBE is just the voltage drop, 0.7 volt. So design the circuit to obtain a emitter current of 0.5 milliamps, emitter bias current of 0.5 milliamps here, and a VC of 6 volts. So VC is the voltage here, right? The DC voltage here, bias voltage, has to be 6. Okay. Now VCC, which is here, now remember when this says 0, that's the signal values, not bias values. So for biasing, we use the given VCC as 15 volts. So if that's 15 and VC is 6, then you know you can find the collector current, right? And the collector resistance. So designed for a DC voltage at the base of 5 volts. So here we need 5 volts. And a current through the RB2 of 50 microamps. So the current here is also given. So specify the values of RB1, RB2, R emitter and R collector. Also give the values of the small signal parameters GM, R pi, RO at the bias point. For the calculation of RO, let the early voltage be 100 volts. So that's 740. 741, using this amplifier, find the input voltage, output voltage and overall voltage gain when our signal is given to be 10 ohms, 10 kilo, and our load is given to be 20. So here are all the formulas we are going to use. These are to find the GM, R pi, RO. You can find the VCC, I mean either IC or RC, using this collector circuit. On the emitter side, you can use these formulas, also derived from a KVL. And then IB is connected to IE, which is given, right, by this. And then for this section, 741, RN, RO, GV, right? So once you have all the formulas, it just is a straightforward application of all these formulas, okay? So RB2 is 100 given IE, hence IB is 5 micro. RB1 becomes VCC minus VB by IRB1, which is 182 kilo ohms. Our emitter using this formula comes out to be 8.6 kilo ohms. Our C using this formula comes out to be 18 kilo ohms. IC is 0.495. Okay. GM, R pi, RO, easy application of formulas. So that was 740. 741, Rn, same formula, a parallel formula, RO formula, GV, use the formula, and you get minus 557.3. Okay, so I don't want to waste any more time on this because we are running out of time, but as you can see, it's just a straightforward application of all these formulas that we have collected here. Just make sure you understand each of these formulas well, and then you can solve the problem. Okay. All right. Next we have another common emitter, but this time with a constant current source used for biasing. Okay. The signal is a sinusoidal signal. The available supply voltage is VCC is 5 volts. The transistor has beta equals 100. It is required to design the circuit to meet the following specifications. Rn is given. Remember, these are not questions, these are just specifications. That means your design has to meet all these conditions. So there's an Rn of 10 kilo that has to be met. The DC voltage drop across RB has to be approximately 0.2 volts. The open circuit voltage gain from base to collector is the maximum possible, consistent with the requirement that the collector voltage never fall by more than approximately 0.4 below the base voltage. That means the transistor must always continue to be in active mode, with the signal between base and emitter being as high as 5 millivolts. So if the signal here cannot exceed 5 millivolts, then find the appropriate design. That means find the values of I, this biasing current, RB and RC. For these resistors, use the 5% resistor values. Lastly, if you're given these resistances, what is the overall voltage gain? Now remember, active mode is, the VB minus VC has to be less than 0.4 volts. Alright, so that's this design problem. So given condition is IBRB is 0.2, IB comes out to be, or this IRB is 20.2. So we create two conditions. Find IRB. Given Rn is 10 kilo ohms, Rn has this formula. So Rn can be written like this. Rn is given. So if you manipulate this IRB is derived here as 20. So if you substitute that IRB, you can solve for RB. Based on that, you can then solve for I. Okay. So we've derived the biasing current I. We've also derived the IB. Then to find IC, collector voltage active mode, this condition has to be satisfied. Instantaneous collector voltage VC equals this. If VB signal has to have a maximum value of 5 volts, then VC is the bias VC minus the amplified 0.05, right, at the collector. This is the open circuit voltage gain. So instantaneous base voltage has to be this, corresponding to this. So consider the condition VB, active mode. You can rewrite this equation because VB is this, VC is this. You can rewrite this condition and solve for VB and VC. But first you solve for VB, and from there you can write this expression for VC. Now AVO, the gain, you can use this formula or this, and in terms of RC it comes out to be this. So plugging this into equation 1, you can derive RC. So summary of what we have found: we found RB is 91, RC is 22, and I, which we just found as 0.2 here, right, 0.22 milliamps. Sorry, it went under. That's what it is. So overall gain is this, and then the other parameters are here. Assume R0 equals infinity. You can get GV as minus 30 volts by volt. Okay, so that is this problem. Now I have another exercise. I know we have run out of time, so I'm not going to walk you through this. I'll let you look through my notes. They should be pretty simple. For a previous CE design, we now introduce a resistor in the emitter. Then what happens to the parameters Rin and gain? That's one exercise. Here's another problem, 7129, also with an emitter resistance. I think this is pretty easy to follow. Just use all these formulas and you can solve it. I have one example of a CB design. I will also let you look through this. If you have any questions from my notes, let me know. There's a collector emitter follower example, and there's one more. So these are solved here. Look through them. I think my notes are pretty clear, and if you have any questions on these, I don't see that there's any complications here in any of these. They are pretty straightforward application of all the formulas. So I'll wish you good luck. Please take time to spend on these examples and problems and make sure you understand each one. Okay? Thank you. Good luck.